Hi, I'm Charan, and this is regarding the ICP5 Big Data Analytics. So, the challenge for this ICP is we have to take a base CNN model and then we have to change the 4 hyperparameters in the source code and report our findings in detail. So before I go on with this, so we'll be using CIFAR dataset as given here. So I'm just mapping them, showing randomly about 25 images, which is from 300 to 325 images. These are the few images of that. There's a bird, automobile, automobile, bird, automobile, and so forth and so on. Well, even before going this, since this runtime of this system is on the collab is quite some time for this notebook, I will show a run execution. But then while it's running, I will be walking you through the code. As you can see, the code starts running, and while it happens with the training, I'll show. As you can see, this is an epoch. By default, the batch size, if you haven't given, that is 32, but this is the same batch size I've given. This is a base model that is asked to replicate with CIFAR dataset and show how this works, and this is an example for it. So while outputs from this is being cleared out, I would like to show outputs from this. So this is a sequential database, sequential layers that I've applied on the base dataset, and as we can see, there are 10 steps of levels completed, and the graphs is like this. As we can see, the model accuracy, the training keeps increasing, and the validation is somehow also increasing. So although we can say the model is trying to fit the training data, because we don't see a significant decrease in the validation accuracy, we cannot treat this really as an as a overfitting data. The second is data augmentation. Now we are able to augment the data, and as we can see here in the plot accuracy, we can see the augmented data, the training, and the accuracy results. The training results accuracy has come down a little because of the amount of data that's passed, but we can see the validation accuracy is doing decently enough. And as it stands, the validation accuracy for the base model is 73%, and for the augmented data is 66%. So these here are some changes that I would like to introduce. These changes are changing the hyperparameters. First is learning rate, and the optimizers change, and here I'm using stochastic gradient descent, which, as we can see, is a method of optimizing the object of the function with suitable properties. Okay, so as part of this, I've also given the decay rate and decay components and the learning rate as well. Learning rate is how fast the weights has to be improved, that or to be learned. That's the learning rate is all about. So I've kept the rest of the factors same in terms of epochs and the batch size, so as to see what is the significant update or increase as a result of this. And as we can see, the model accuracy was about 67%, and the training accuracy was about 81%. And the next hyperparameters change is epoch and batch size. So I've increased epoch to 2 times, that is 20 epochs, and batch size reduced to half, that is 16. So I have fed in the 16 batch size, which is, as we can see, has run for 20 epochs, and the validation accuracy is 71.39, but the training accuracy is about 93.06, the highest of the training accuracy across the models. This shows with more epochs available, the model itself has turned as an overfitted model. It's trying to fit the training data as much as it can, but it has not shown significant improvement on the validation data. So we tend to see these type of models as overfitting models. The next one is binary cross entropy. I wanted to change another hyperparameters, that is the loss function. So the reason for applying the binary cross entropy is to prove that binary cross entropy will perform very bad on a multiple classification problem, because binary cross entropy is a combination of the sigmoid function, which is used for a binary classification, and then and a combination of cross entropy loss. That's what the binary cross entropy does. That's where I wanted to prove my hypothesis that this is a worst performing model based on the loss functions, and how a significant loss function keeping the rest of the parameters same can influence the model. And as I can show, the validation accuracy is 10%, and the normal accuracy is also about 10%. So this is a very bad example of performance for the model. As we can see, he is straight dipping down. It's all in 10% range. And going towards the activation function, that's the next hyperparameters I'm intending to change. Softmax is a multi-class probability function, which is an extension to the sigmoid. And using this softmax, I've used the last layer to have the activation function as softmax, because the classification is across 10 outputs, and I wanted to see each output as a probability number as a result from the softmax function, and the combined probability would be 1%. So using this, I've trained, keeping the rest of the parameters same. I've trained this, but as we can see, the model has not significantly increased. It's about 67% of validation accuracy, and accuracy is about 69% of training accuracy. But since looking at the validation function, we cannot really call this a overfitted graph. So this performs decently, but it doesn't stand up with the base model that we have already used. And the last experiment is to change the dropout layer. Dropout is keeping some amount of neurons inactive at the time of training, in order to ensure the model is not overfitted with the training data, and it remains robust for the different types of outliers that are present in the training data. Looking at this is 30% of neurons I have asked to be in the turned off mode at any point of time during the training. Based on that, as we can keeping the rest of the parameters same, like epoch and the batch size, we could see validation is about 73.39, the highest of all validation accuracy. However, the training accuracy is not significantly improved, but we are usually overly concerned about the validation accuracy or the test accuracy, not that we wanted to fit our model in the training. So overall, I've considered dropout as the best performing one, but given the insignificant increase in the accuracy levels, I cannot conclude saying this is the only best available combination. But I see with dropout and more epochs, maybe there is a chance that it could improve better. There's a note here, just to mention, I have done these experiments on top of the base model, because the base model, because of the limited computing resources I've got available, and I've seen lots of timeouts happening in the Google Colab at the time of training. These are the performance. These are different performance, as we can see different performance models, and these are my conclusions that I've arrived. Using the binary cross entropy, I've shown the worst performance, because this is to prove my hypothesis that binary cross entropy function is a very bad combination for this. Change it to the dropout layer, and to avoid the overfitting, as we can see with more epochs, we've seen there is a case of overfitting. So as to prove that with dropout, the overfitting can be reduced, or overfitting can be controlled, to make sure the model can be robust. I've made 30% unavailable for during the dropout layer. That's how this model has shown the best performance. And I've implemented the softmax function. While softmax function has not improved any accuracy, but it has significantly decreased about 7%, keeping the rest of the parameters same. So I conclude that ReLU is the best to understand the convolutional neural networks given the nonlinearity of the functions. And with more epochs, I also observed that there's a trend of overfitting in the models. And like I've explained, it has also demonstrated in the graphs. And like I showed, these are the few references apart from my conclusions. Going back to the Google Colab, I wanted to show the training process from what we have pastly done. And the model is still training on the first parameter, as we can see. This is 10th. I'll hopefully wait for this to finish so as I can show the plots of this one. There is still 500 more steps to be finished, which should be done fairly quick. And here is the plotting that I'm doing to see the validation accuracy and the model and the training accuracy. Now that model is finished with the training, as we can see the graphs, and the subsequent models are getting trained. Thank you so much.